So hi, yeah, thanks for the intro, Neeraj, and I just want to take a minute and thank our awesome organizers and volunteers for putting on a really great conference. I'm super excited to be talking to you about the work we're doing at Databricks, formerly MosaicML, training large language models, and I hope at the end of the talk I can kind of impart you with a few tidbits of wisdom that we've learned, and so you can kind of, it's great to see everyone here has been trying to train LLMs themselves. So we're going to cover, first of all, just really quickly the value prop of generative AI and generative models, a little bit about the type of LLMs that we're working with. I'm going to talk about MPT, which is an open source model that we put out earlier this year. There have been a lot of really awesome models that have come out since then, so that might be a little stale, but it really kind of speaks to how quickly the field is moving. And also how we trained it on the MosaicML platform, and then breeze through right to the lessons and gotchas that we've got there. So first, what's really all the rage here? I think everyone here, and just looking at the conference agenda, we can all agree, we really think the hypothesis here is that generative AI will transform how we do business. It'll transform our daily lives, it'll transform how we interact with computing systems, and we really look at this on kind of three different levels. First is we're going to be able to converse with computers. Finally, right? I mean, I grew up watching Star Trek: The Next Generation. You always want to talk to the computer and have comical interactions, but really this is today. We're living this now. And it's really going to increase productivity. It's going to change the way we interact with these computing systems. The other is we can have human level comprehension at the speed of computing, right? We can actually process billions of tokens of text. And this is really just going to drive new levels of insight. I mean, imagine financial analysts that have to sift through like dense SEC records that are coming out constantly to gain an edge. This is just going to get faster, right? These things are prone to just scale. And lastly, I think the thing that really excites everyone is generative properties, right? Generative capabilities. Being able to generate human quality text, images, video. We got systems that are actually generating code now. And so this is really just going to take human productivity and creativity to completely new levels. But why would you build your own model? Why would you actually want to go through the pain of training a model? For some folks, it's probably not for you, right? There are other techniques. You can find a lot of really great open source models and a lot of other proprietary models that are hosted behind some type of API. When customers come to us and they want to train their models, they really come at these kind of four levels. First is privacy, right? You have very sensitive business data. Even if you want to send the prompt to an open source or a third-party model, you don't really want to expose that. There are also well-documented cases of lots of breaches. So you really have sensitive data, and you don't want to send it to someone, right? So you want to host it yourself. Now, if you want to host it yourself, you really have to deal with the other three things, which is quality, cost, and latency. So quality is potentially a capability that I don't have, right? Or I can't get from another model that's out there. I was kind of thinking about this, like if you're trying to build like the Large Hadron Collider, imagine what the user manual for that thing is. I'm pretty sure ChatGPT, I haven't tried it, but I'm pretty sure ChatGPT is not going to be great at telling you how to use it. So you want to impart it with some knowledge or capability that you don't already have. The other side of quality is actually related to cost and latency. You might not want to train a trillion parameter model. It's actually really, really expensive to train and host a trillion parameter model or a 500 billion parameter model. Can you do it in 3 billion parameters and host it at a fraction of the cost? And you have tight latency requirements. You don't want to wait forever to prompt it and then wait an hour and come back. You actually really want it to be responsive. You want it to engage with a high volume of users. So really those three dimensions are very related. And we've actually already proved this time and time again. So these are really 4 customers across a variety of use cases that we worked with. MetaDialog wanted to train a chatbot on an Arabic data set, right? This is not really something that's has been very common. And so they've actually trained a model with us and they've deployed it. It's in use now. Replit is the highly publicized one where they actually started with, I think, a 3 billion parameter MPT model and trained it for code generation. And it's already deployed and in production. Petronas trained a model to identify personally identifiable information, so you can prevent business data leaks. And HyperWrite really made a writing assistant that can do auto translation and other generative capabilities. And so all of these folks, really had to deal with those 4 things I talked about earlier. And they came to us and said, hey, can you help us train? So let's talk about Really quickly, LLM. So here I'm talking about decoder-only based LLM. So if you've read sort of the seminal paper on this, attention is all you need. There's really a few different variants. You can have encoder models, you can have decoder-only models, you can have encoder-decoder models like T5. Encoders would be like BERTs, and decoders are like your GPT style. So when we trained MPT, decoder models are really all the rage. So we trained an MPT open source model that was based on a GPT architecture. But what is an LLM really doing? It's just predicting the next word, right? It's given an input sequence. What is the likelihood of the next word? And it puts out a probability distribution, and then we have kind of fun ways of picking which word we should go with. We call them autoregressive because we put a loop around it, and what we do is we say, give me the next word, let me pick it, append it to the input, rerun, and that's how we generate text until we hit some type of stop condition. Usually it's a special stop token, says I'm done, or you've hit a max token length if your model likes to ramble. But really, let's get to the meat of it, right? Training. And really, this is like if you were growing up reading like Goosebumps or R.L. Stein books, it was like kind of a choose your own adventure type thing here, right? You have really two starting points. First, kind of what I alluded to earlier, is you can pick something that is a known good start, right? It's a pre-trained model. It has weights. It's already been deployed. If you're starting there, you have an option of continuing to pre-train it. And this is a self-supervised process, so really you're going for tokens, right? And we'll talk about the quality of tokens in a bit, but really you want a lot of tokens. You impart it that's representative of the capability or the knowledge you want to bestow on it, or you want it to learn. You can do fine-tuning, which is actually more of a supervised technique, and this is really, hey, I want you to react this way to certain keywords or certain instructions, so common ways of instruction fine-tuning your model. This is when you kind of impart chat-type capabilities, right? Like, here's how a typical conversation would look, or if I want to have system prompts, here's how I want you to behave. And then there's this other technique that's growing considerably in popularity called RLHF. Which is really using either human or model-generated preference data to train other models that then teach the LLM really how you want it to respond, right? What is a good response? What is a bad response? And this is really how you get these really, really high-quality models. And actually, data acquisition step here is also pretty expensive. With MPT, we actually chose the top approach, which is we started with our own model architecture, which we optimized for training, so we used very fast kernels. We started with basically the weights randomized, so we wanted to create our own data set and train our own model. We pre-trained it, we fine-tuned it. We didn't RLHF this one, and then now we were deploying it. So there's two variants we put out early this year, a smaller model at 7 billion and another 30 billion parameter model. But let's talk really quickly about why we decided to go through this, right? Why did we create MPT? Well, for one, at the time, and this has changed considerably since then with like Mistral models coming out and Llama V2 coming out, but we really wanted to provide an open source model for the community that's a great starting point with a commercially viable license, right? So something that you're not going to get sued, hopefully, for using. So we put out several different models here, and we also wanted to demonstrate different capabilities. So most of the models that we put out are commercially viable. They're using a permissive license. We started MPT-7B with a 2K context length, and then we actually retrained it to do 8K context lengths. We also did a chat version of this model. We used the Alpaca dataset, so it was actually generated using ChatGPT. So this version is not permissible commercially, but we wanted to, again, demonstrate that capability. And we also trained a very, very large context length model using Alibi. And that's a 64K model. This was before the 100K models had come out sort of mid this year. And we really wanted to show, I think we wrote a prologue for The Great Gatsby, right, just to kind of show this capability. And then we wanted to up the scale. So we went to a 30B model at 8K context length, but actually using more or less the same data set. So we trained it on about 1 trillion tokens. And again, there are better models that have come out, but at the time, this was a really great model. 7B really, held its own against all these other models that were put out by the community at the time. And we love to look at model evaluation using these radar plots across multiple dimensions. Makes it easy. The larger the area, generally the better the model is across the dimensions that you're looking at. And so 7B really held its own against Falcon and Llama V1 at the time. And MPT-30B actually performed as good, if not better, on certain dimensions than 40 billion parameter models like Falcon. The other thing we wanted to show is we wanted to really just bust the common myths around exorbitant training costs. So we put out a super scientific, just kidding, unofficial social media poll on I think LinkedIn and Twitter, and we said, how much do you think it costs to train a GPT-3 quality model? And I think something like 65% of the users responded and said costs over $1 million, and 80% thought it would cost $500,000 or more. And we actually did it. We actually did it for MPT-7B in $250,000. And that was a pre-training cost. This is on 1 trillion tokens. And for a few $1,000s more is what we actually did to fine-tune it. And if you've had a chance to use it, it's actually pretty good. With a 30B, it's a little more expensive. We'll talk about kind of why this happens. But on an A100, you can actually train it for still under $1 million. And on H100s, it's actually a little more cost effective. I got actually our NVIDIA person right here, so I got to talk good about H100s and A100s. And then fine tuning, it's, whatever. This is, a nice group dinner. So it really doesn't take that much money to customize these models. The other thing we were doing is we actually had to build a platform to do this. And that's at scale, right? I'm talking about training on 512 GPUs. We actually train on considerably more now. You gotta be able to manage these things at scale. And so we had built this training platform, and we really needed to battle test it. And so what does this platform let you do? Well, it's a fully high-performance, vertically integrated training stack. First of all, it lets you do science. It integrates with all your popular experiment trackers. We provide all the high-quality models through something called the LLM Foundry. And this is all the tooling that you need to train, all the examples to pre-train, fine-tune, whatever you want. Prep your data sets. We also do fast deterministic data loading at scale, very cheaply. You don't need expensive network-attached storage anymore. You can just stuff it in an object store. And now with Databricks and a UC volume and the stream at relatively low cost, and we also efficiently manage egress fees. If you're training within cloud providers, you don't actually worry about those. If you're going cross-cloud, we only download and access data when we need to. So we're not downloading full data sets multiple times. We do automatic model checkpointing and resumption. So if you have a hardware failure, we'll stop or restart. You will barely see a blip on the screen. And I think the most important is really just doing things at scale, right? Going from 1 GPU to 8 GPU to 512 GPUs to 1,000 to 4K. We wanted to make it so simple, you just change one line, and in fact, our dream is to really just automate that away. You don't have to worry about it. You just tell us how long you want to take to train. And then all the orchestration, scheduling, and stuff on top of that. So this is what the stack looks like. So we integrate with weights and biases, Common ML, ML flow. It's very easy to add other experiment trackers. This is all kind of sitting on top of the group that I lead, which is what we call our ML runtime team. And that is the group that actually develops the LLM Foundry, the streaming dataset library, which enables fast data loading at scale, and Composer, which is our distributed training framework. And it's all built on top of PyTorch. And MCLI is our paid platform layer, which does the orchestration, scheduling, fault tolerance, fault reporting, all the stuff at scale, and built on the best accelerators money can buy. And lastly, we wanted to learn, right? We wanted to figure out what went wrong. What are we doing that's not exactly the smartest thing? But we wanted to do it so you guys don't have to learn the lessons the hard way. And so let's get into what we learned doing this. First, create a plan. I was actually wondering if Ben Franklin actually said this. Apparently, the jury's still out. But let's pretend he did. And so really by failing to prepare, you're preparing to fail. And so the first thing you really want to do is define your problem, right? And I know maybe I sound like a broken record here. Good engineering is all about defining a problem that you want to solve. And really, what are you trying to accomplish with an LLM? And I would also ask yourself hard questions. Do you need an LLM? Don't use an LLM if you don't need an LLM, right? Use a smaller model, because you're really signing up for quite a bit here if you really want to drive accuracy, cost, and performance. So if you can solve this another way, do it. But let's say you have a business goal. You really want a generalized model. It's good at multiple different things. And for the sake of it, let's say, hey, we want to create a high-quality coding assistant, right, for our software engineers. Well, how are what capabilities do you need to be successful? Well, I want it to convert text to code. So I want to give it a task and it'll generate code for me. I want to comment the code so people can understand it later. And I also want support for C++, Go, and Python. For anyone that's dealt with code generation platforms that aren't intelligent, you'll know that this is actually amazing, right? Because it's human readable, but also usually functional. And if it's not, you can feed it back in and it'll actually correct it for you. But this is the most important part, right? You need to define your problem to understand how to quantify whether or not you're going to be successful. And this is not a talk on eval. You could probably have potentially a whole conference on eval. But come up with a way to measure your success. Identify evaluation criteria and metrics. So in this case, we want to do a code generation model. You should probably use human eval, which is a bit of a misnomer. There's no humans involved, but really it's an eval suite out there that tests the quality of code generation. And we also offer a lot of tooling that just kind of lets you run these types of things. In-context learning is another popular eval suite. You can actually create your own evals. You might also want to eval things for bias, toxicity. Definitely find user cases that are unique to the challenge and the problem that you're trying to solve and create evals around that. At Mosaic, we also like vibe checks, right? These are conversational systems. Talk to them. We love during our training runs to have things like, if you were an AI model, what would you name yourself? And see what it responds with. We do the banana bread test, where one of our engineers decided to ask various different models for banana bread recipes, and then we actually cook them and eat them and see how they are. Have fun with it. But these are things that you're going to be using in ways that you're not used to using computing systems. It's a lot more like interacting with humans. So have a way of judging them. Have a way of quantifying that and understanding your success. The other is performance KPIs, right? We talked about cost and performance. Try to understand these in the context of the problem that you're trying to solve. Now let's talk a little bit about budgeting. First, I want to train a model. I got to figure out how much data I need. How much data do you have? Do you have enough data? Do you need more data? So how do you do this? Well, we actually started with scaling loss. So we love chinchilla scaling. And really, this is a great starting point. It's not all that you need. And I'll talk about that, but bear with me for a second. Really what this is trying to answer is, what is the amount of data that I need to hit a certain quality target at minimum training cost, right? And that's really kind of what Chinchilla is working on. And so here what we're going to do is we're going to use scaling laws. They're a pretty straightforward equation. Please read the paper if you haven't. But really a simple equation to figure this out, right? And so if I want to train a 30 billion parameter model using this equation, I need about 600 billion tokens to do that. Now, the chinchilla scaling laws also can give you a little equation that you can use to predict loss. So I can use a 30 billion parameter model on 600 billion tokens. If I actually wanted to say do a 175 billion parameter model, I actually need about 300 billion tokens to do that. That's to hit the same loss value. I haven't written that equation down. It won't work if you plug it in here. So if I'm just looking at loss, that's kind of what chinchilla scaling is looking at. The next thing I want to look at, and we'll remember the 175 billion example in a second, because really it comes down to inference, right? Hosting a 175 billion parameter model at roughly the same quality as a 30 billion is going to be considerably more expensive. So don't just think about training, think about the cost of inference. When we first started, we actually didn't. And it turned out we trained really expensive models, and we found out they were really expensive to host. And we found other customers do this. So think about not just, and this is where Chinchilla stops, right? Chinchilla thinks just about training, but really what you want to look at is training and cost. And often what you find is you can actually train a smaller model on considerably more data to get a lot more accuracy. And it'll actually be cheaper. So you're not training compute optimally, but you're going to train for longer to get better accuracy. Can we just do questions at the end? Yes, sorry. But you also need good data, right? And let's talk about compute time and cost trade-off. So let's think about how much time it's going to take to train. So if I want to train a 30 billion parameter model, I can use this approximate equation to figure that out. And really a 30 billion parameter model is going to take me on 600 billion parameters, is going to take me about 3,000 H100 days. And it'll cost about $500,000 to train at $7 an H100 hour. And this is not, this is like plus or minus probably like 10, 15%. Keep in mind, this is also your long training run. You're going to do lots of other smaller training runs to experiment. But roughly, that's kind of how you get there. So now you have your budget. You know how much compute you need to go after. And now let's talk about experimenting. Experiment. You're not going to find answers right away. So first of all, don't trust anyone. And I'm not trying to come off as a very, very paranoid person, but I am. Don't trust anyone. You go to conferences and someone says, so-and-so works for me. You guys should do it. Don't bank millions of dollars on that thing. Try it yourself. Break it down as a small experiment. Things are data distribution dependent. Things are, could be different from different model architectures. Some things are great. Some things will not work across the board. So don't trust your intuition. Don't trust literature. Don't trust anything else. Do not bank a multi-million-dollar training run on things that you haven't tested. And so question, experiment, test, measure. The great thing about scaling laws is things that tend to work at smaller scales actually kind of extrapolate fairly well at larger scales. But even during your training run, have stop points. Stop somewhere, check if it's doing what you're expecting. If it's not, stop, right? Limit your loss, go back, and try again. Leverage good starting points. So I know I said don't trust everyone, but there are good starting points. And the reason for this is actually focus on the things that you really need to focus on. You don't need to invent a new model every time. Maybe the problem you're solving mandates that you do, but most people don't need to invent a new model every time. We spend a lot of time optimizing models. We're really good at it. Please use them because you will actually get the best TCO if you do. So there's a lot of great things. The Foundry, Llama V2, GPT-NEO-X, there's a lot of amazing open source models out there. Use performance model optimized and things that are numerically stable, by the way. And as I said earlier, start small, right? You don't need to start, don't go to your VP or your CIO and say, hey, we're going to train a 500 billion parameter model at 99% quality on these metrics. You're not. It just doesn't work that way, right? Start at 1 billion. Solve a problem, solve 3 billion, scale up as you need, right? And I would even say before you even start training, right, try other techniques. Try RAG, retrieval augmented generation, try prompt engineering. It might be good enough for what you're doing. And mistakes cost a lot more at scale, right? So that's why I'm saying limit your loss. And iterate quickly, right? The speed of iteration here is not like traditional software engineering. You don't just come up with a spec, go scrum it, call it a day. There's a path here that's actually a little bit unbounded. You want to be able to iterate quickly. You want to answer questions. You want to quickly ask questions and come up with answers. All right, lesson 3, data. Garbage in, garbage out, right? I mean, this is true for LLMs. It's been true for classical deep learning, classical machine learning, everything, right? You really depend on the quality of your data. So first and foremost, experiment the mix that you want. And this is all defined by what you have, what problem you're trying to solve, right? But where you're going to get it, right? This is a token game. So you need 500 billion, 600 billion, 300 billion, whatever tokens. You're going to go crawl the internet. There's publicly available data sets that have done this. These data sets are not great, actually. Some are better than others. You're going to go after textbooks. You're going to go after academic, right? Try to figure out, again, which capabilities that you want. If you're going after open source, make sure it's permissive licensing. There's just a lot going on in terms of, because everyone's playing the token game, of using copyrighted material. Make sure you filter for those types of things. Experiment, and then one thing that we like to say is keep your training and test data separate. There's some research out there that's saying this probably doesn't matter as much for LLMs, but really it's a little sketchy when you train on your test data. It's learned it, so until we really know that it doesn't matter, just keep your training and test data separate. So as I said before, data set processing. You're going to spend a lot of time doing this, maybe more time than training. You're going to clean, right? So there's a lot of repeats. There's a lot of toxicity. There's personally identifiable information, depending on where you're getting your data. You might have encoding issues. You don't want your model to, if you're especially building your own tokenizer, you don't want it to learn on poor encoding. You're just wasting compute. So spend some time cleaning your data. Deduplication helps, right? People tend to copy a lot of things on the internet, then we crawl them and there's copies. You don't need all those copies. It actually helps and it reduces your token count, which ultimately reduces your cost. So remember, what we try to do at Mosaic and Databricks is really try to minimize the amount of data. It is in a way a speed up method. So deduplication really helps you get there. Pre-tokenization and concatenation. A lot of folks actually tokenize on the fly. You're wasting compute. We've had really great success just pre-tokenizing all our data sets. It's actually very fast. And concatenating them. So if you have an input length and you're training on 2K, don't pad it. Concat your data sets together so you're actually getting every cycle of compute you possibly can. Computing on zeros doesn't really help the model learn anything. And shuffling. I cannot emphasize shuffle quality at scale. Ideally, you want each batch that you're training on to include a diverse set of samples. You want it to be a good sample and representative of your data set. Representative distribution, and it's really in a way it's a regularization. If you don't do this, and we've done this many times, we get what we lovingly call wavy boys. And really it's just a very noisy, spiky loss curve, and you don't want this, right? You actually want a really nice smooth curve. I have an example of one later. And so you see something like this, suspect your shuffling is potentially pretty poor. The other, we, believe it or not, did not do this. We were not data engineers and data scientists to start. And when we started processing data, we just got paid for these two really beefy machines and wrote our own distributed Python implementation to process data. It took us days, if not weeks, to just do the most basic tasks. So invest in scalable data exploration, preparation, ETL architecture. We are now partially forced now that we've been acquired by Databricks, but also in a great way, we have this awesome ETL processing tool and data processing tool. And what we were able to do in days or weeks has now been reduced to mere hours, right? Doing this using Apache Spark. So make sure that you build this proficiency if you don't have it, hire the folks, learn it, whatever you need to do. Let's see, 3 minutes. Sorry, I'll speed up a little bit. So scaling is hard. You're going from 1 GPU to tens to hundreds to thousands. You need to do that, right? So if you start with 3,000 days with the example I was doing earlier, 512 gets you 6 days, 1024 gets you 3 days. But to do this, you need really strong linear scaling, right? So depending on the parallelism strategy. Again, this is not stuff that you need to build. You also don't need to be super complicated here. At Mosaic, we actually go with a relatively simple parallelism strategy. It's built into PyTorch called FSDP. I think it was kind of pioneered by some of the folks at Microsoft with deep speed. But this scales really, really well. And it scales really well if you have a fast interconnect. Now, things are going to go wrong at scale, right? Your software is going to break, your hardware is going to break, something's going to happen. Rule of thumb, we generally see, this is not something we've measured, but we try to do, kind of look at this here, is that you're going to see about 1 failure every 1,000 GPU days. And these failures at this point tend to be disruptive to the job, right? The job will just die. So allocate spare compute resources. But usually, if you see something, it's really these 3 things. And really what I'm building up to here is just pick a platform that handles this for you. And this is sort of my case to say, come train with Mosaic, but there's other people that do similar things, or pick 2 or 3 of the best things, put them together yourself. But you really don't want to have to worry about, this version of PyTorch, or this version of CUDA, or so-and-so. Just someone's figured that out. I have very smart people on my team that are very good at this, and they enjoy it for some reason. Scheduling and orchestration, right? You need a good platform to handle that. Model checkpointing, basically everything I told you that the Mosaic platform does. And this is really the thing that killed it for us, which is we ran MPT 7B, and we had hardware failures, but our log was clean. If you go compare that to like the OPT log, like this was literally just like, hardware failure, we checkpointed, we're resuming, we keep going. Takes maybe 20, 30 minutes max, and this scales really, really well. And the last thing I'll leave you with is process and discipline, right? So this is not the technology. This is kind of, I think, I'm talking about intro. I come from a place where I build chips, and so, if you think about building chips, you're spending tens of millions of dollars to tape out. You need processes to make sure that you're limiting your risk. And this is really what happens, right? Have a pre-flight checklist. What are the things that you need to do before you're comfortable hitting go on a $5 million or $1 million or 500K, depending on what scale you're doing? So, go through these, build them for your organization. We'll probably put one out that you guys can, we might even write a whole blog post on this that you can just pull. Designate a training run on call, right? Technology is great until it fails. So you need someone, a human, to be on call to pull the right people in when things fail. And lastly, keep a log and learn from that log. right? If you're going to do this again, you want to build a process that lets you do this very efficiently. And that's it. So I think, thanks for listening. I will maybe just skip over the final remarks, but yeah.